Good morning, everyone. Welcome to the fifth lecture for this workshop. Today, we would be exploring the symmetries using the Geogebra app and studying about strip patterns. Professor Geeta Venkataraman has joined us for the same. We welcome you, ma'am.
Thank you. So should I start now?
Yes, ma'am, please.
Okay, so first I want to complete something that I couldn't finish yesterday, which is I wanted to do the proof of Cauchy's theorem using group actions. After that, I will try and tell you more about how to use GeoGebra to explore symmetries. And so let's get started. And I'm going to start because this was something I actually wanted to do yesterday, but we ran out of time. So this is Cauchy's theorem. And some of you may be familiar with it. It basically says that let G be a group and let P be a prime such that P divides order of G, then there exists an A belonging to G such that order of A is P. So you can think of this as a partial converse to Lagrange's theorem. The converse question there would be that if D divides the order of G, is there a subgroup of order D? And what Cauchy's theorem says is that if you look at if your divisor is a prime, then the answer is yes. You can find an element which has order P, and so the cyclic subgroup generated by that element is going to have order P. Now, most of the proofs that you may have seen probably do this by induction. First prove it for abelian groups and then for groups in general. But here what we're going to do is to use group action, and I'm just going to explain the idea first and then we'll look at the proof. And this proof is due to a mathematician called James Mackay, and it was published in the American Math Monthly. This is a variation of it. So what you have is this group G, and you know that P divides order G, okay? And somehow you want to find an element A such that when you look at A raised to the power, so you want an A which is not equal to identity, and A to the power P should be identity. So you think of this A to the power P as A into A into A P times. And so your search for such an element takes place in the following set. The set X is simply G to the power N, as in the Cartesian product. Well, it's a subset of this. And what does it consist of? It consists of, so X is defined as the collection of all X. I'm going to put X0 because you'll see why I want to do this a little later. X to the power P minus 1 belonging to G to the power N, with the condition that the product is identity. Okay, so your X, I'll write it down better here, consists of all these P tuples. I've started with 0, so there are P of them. each entry is coming from G such that their product gives you identity. Now, and obviously, well, we are going to get some group to act on X, and using that, we are going to be able to find this element that we need in G. Now, how is it connected to this thing? So for that, see, the idea is that you have an action of a group which is just going to move this in a cycle. Okay, and obviously the best group which is going to do that. So the group that you want to look at is ZP. This is your group, and what does this consist of? 0, 1, 2, 3 up to P minus 1 under addition modulo P. And what you can see is that if I take so ZP acts on X as follows. And what's the action? If I take an I belonging to ZP and an X, let me call it X bar, or maybe not, let me, okay. It's okay. So let's say this element X0, X1 up to Xp minus 1 belonging to X, then what will I of X bar be? It's just going to be X0 plus I, comma X1 plus I. So you'll have to go modulo P. Okay, this addition is mod P. So you want to take the remainder on division by P, and all the way up to X of I plus P minus 1 mod P.
Okay? Ma'am,
yeah.
Ma'am, you have taken P minus 1. So how is it a subset of G to the power N?
So each Xi belongs to G.
Yes, ma'am. So there are P in number, no?
Oh, sorry, P. Thanks so much. Yes. I don't know where the N, you're so used to thinking of the order of the group.
Yeah,
N. Well, the group could have order N, P divides N. So thank you. Yeah, it's G to the power P that we are looking at there. Okay, so now if you look at this thing, basically what it's done is it just cyclically moved the elements of this the initial element that you started out with. It's just cyclically rotated the coordinates, because what this will turn out to be is xi plus 1 ... You'll reach xp minus 1 and then x1 all the way up to xi minus 1. Okay, so this is precisely what happens when you apply I on X bar. And you can check that, verify that this actually again belongs to X. That is, if you multiply this, you will again get identity. Okay, so you do get an action of ZP on X. Now, how is it connected to finding an element of order P? Now, the point is that well, I mean, so we'll come to that. Basically, when I if you see the x0, x1, x to the power p minus 1, if we want to find an element of order P, basically what I want is an entry here which has A in every coordinate, A not equal to identity, right? Because the moment I can get an A comma A comma A comma A here, what I will get is that when I multiply all copies of it, I'll get A to the power P is identity. And as long as I can find, so the aim is to find an A bar equals A comma A comma A belonging to X, where A is in G minus E. Okay, so that's our aim. And somehow using this action of this group, we are going to do that. All right. Now, we are going to utilize several things. Okay, so first let's look at what the order of X is. So what will the order of X be? Can someone tell me? Remember, this is all those x0, x1, all the way up to x to the power p minus 1, with the condition that each xi is in G and the product gives me identity. So can you tell me what the order will be? Sorry, this was X. So I should. So take a guess. What do you think the order will be?
Ma'am?
Yeah, after ma'am, something else has to be said.
Ma'am, I was asking, how did you write I dot x bar like the way this x0 plus I?
That's just the definition.
Okay, ma'am. Okay.
So I'm defining the action to be like this. And if you just work out all of this, it'll be like, you know, so you think of your x0, x1, x2, xi plus 1, all the way up to xp minus 1. So basically what zp is doing is that it's just moving x0 to the xith position. The first coordinate to the ith coordinate. And then obviously the ith coordinate moves up and so on. So that's basically what's happening here. It's just rotating. If you're starting your, your ordered pth, the ordered p tuple with x0, when you apply I of zp to it, you'll start the tuple at I, basically. And it goes like that. That's essentially what's happening. So if I apply 1 to 0 to x bar, so for example, 0 times x bar will always be just x bar for all x bar belonging to x, right? Because it's not going to move those things around. However, if I take 1, when I apply 1 to x bar, my tuple will start with x1, x2 and go xp minus 1 and then x naught. That's the action of 1. When I apply 2, it moves 2 places. When I apply 3, it moves 3 places and so on.
It's basically shifting the coordinate.
It's shifting in a cyclic way.
Cyclic way, yes.
Yeah. So that's basically what the action is, right? And you should start thinking that suppose I pick a tuple x0, x1, xp minus 1, and I want to know which I can be in its stabilizer. Remember, an I will belong to the stabilizer if and only if it fixes that tuple. The value of the tuple has to be the same even after the coordinates move, right? So what kind of a tuple will be fixed by a non-zero I? Just think about that. But in the meantime, I want somebody to tell me how many elements will there be in X. So can I choose all P minus P of these coordinates independently?
Ma'am, we can choose P minus 1 elements and take XPI minus 1 to be XPI minus 2 inverse, XI minus XI, X1 inverse and X naught inverse, the product of these.
Yeah, correct. So the point is you can choose the first P minus 1 independently, and then this value will get determined by this equation, right? Because xp minus 1 is nothing but xp minus 1 will be nothing but x0, x1 all the way up to xp minus 2 inverse. Okay, so these you can choose independently. In fact, this equation is the reason why this actually turns out to be an action as well. Right. So what is the order of X? I have order G choices for the first one, order G for the second one, and order G for the P minus 1 thing. So this is going to be order G
to the
for
power
power P minus 1. Right. So that's the order of X. Okay. And now let's examine the stabilizer. Okay. So let X bar equal to x0, x1 up to x p minus 1 belong to X, and I want to know what are the things which sit inside stabilizer of X bar. Okay. As I said before, 0 will always, it's a subgroup, right? This is a subgroup of ZP. Therefore, stabilizer of X bar will always have 0 in it. But can it have a non-zero I? What should be the condition on X bar such that a non-zero I belongs to stabilizer? Okay. So let I belong to ZP minus 0. Okay. Then I will belong to stabilizer of X bar if and only if, okay, I should mention something here. See, stabilizer of X bar is a subgroup of ZP, right? So what can its order be? Order can be either
1 or P.
order P. It's either 1
Or P.
or P. So
1 or
basically,
P.
so which basically means that for any X bar, stabilizer of X bar is either 0 or stabilizer of X bar is the whole of
ZP.
Right? So, so in a way, actually, I suppose, let me state this question in a better way. What I'm saying is, I'm asking what are the X bars, if at all, for which the stabilizer can be the whole of Z. What X bars will have stabilizer Can someone mute whoever it is? Someone's mic is on. Yeah, thank you. So the question is, which X bars, which X bar will have stabilizer of X bar equals ZP? So again, take a quick guess. Remember what the I is doing? It's just cyclically shifting the coordinates around. but we want them all to be in the stabilizer. So we want them all to fix x bar. So what will x bar have to be like if it has ZP as its stabilizer? I mean, see, suppose I tell you that x0 is not equal to x1. Then can it have any I in its stabilizer? Suppose I write an element which is AB, AB, AB. Okay, say. And if I apply, what happens if I apply 1 to this? So if this was my element, okay, so if this was my G and I apply 1 to this G, then what does the, so this was your x0, this is your x1, this is your x2, x3 and so on. This is your xp minus 1. So what happens when I apply 1 to G? This moves, right? x0 will move to the 1th position. So I'll end up getting BA, BA, BA and so on. And if I want 1 to be in my stabilizer, I'm saying that these two coordinates have to be the same. These two p tuples have to be the same, right? So the point is when you're taking an x bar which is x0, x1 all the way up to xp minus 1, and you're looking at 1 times x bar, that will give you x1, x2 all the way up to xp minus 1, x0. Okay, you want these two to be equal, which means x0 will be equal to x1, x1 will be equal to x2, xp minus 2 will be equal to xp minus 1, and xp minus 1 will be equal to x0. So can you see that from here? So because, and then remember what 2 times x bar is. That's nothing but you're starting with x2,
x2 and x1 will be
all
the
the way
last.
up to xp minus 1, and then x1, and then x0, and then x1.
x0, x1.
And so on. All the way
All
up to
xi's are
minus 1
same.
x bar. Yeah, all the, exactly. So
They
all
have to
the
be same.
will have to be the same. So, stabilizer of x bar will be equal
All even.
to ZP if and only if x bar is of the form
all.
Huh.
All the positions have to be same.
Yeah, for some A belonging to G. Okay, so this is something that you should remember. Okay, so obviously if the stabilizer is just either 0 or ZP, correspondingly you can write down what the orbit will be, right? That's the other point that you should note. So, so let's summarize this. So given any x bar belonging to X, one of the following happens.
Excuse me, ma'am.
Yeah.
Ma'am, can you please repeat the above step?
Okay. So what I'm trying to say, let me choose a highlighter. So you are starting out with an arbitrary element in your X, which, okay, just start with any element in your X. And what happens under the action of ZP? Each element basically rotates, moves the coordinates around, right? And we know precisely how it moves it around. So when I apply 0 to x bar remains as it was to start off with. But when I apply 1 to x bar, the new element in capital X I get has x1 in its first coordinate, x2 in its second coordinate, and x0 in its pth coordinate. And like that, I've written down all the possible images of x bar. That is all the elements of the orbit of x bar when I have acted on x bar by elements of ZP. Now we separately saw that because ZP is a group of prime order, any subgroup in it has order either 1 or the whole of P. Okay, so if I take the stabilizer of any x bar, it will either have just 0 which fixes it, or it is going to have the entire group fixing it. Now, if let's say, suppose 1 belongs to the stabilizer of x bar, what does that mean? That means 1 times x bar is equal to x bar. That means this particular element of x bar and this particular element of x bar have to be the same. But two p tuples are the same only if their coordinates agree, right? So immediately right from just taking that x bar must be equal to 1 times x bar, you will immediately get, what will you get from these two things being equal? X bar equal to 1 times x bar itself will give you that x0 should be equal to x1 equal to x2 equals all the way up to xp minus 1. That is every single entry. So an x bar will be fixed by the element 1 of ZP only if all its entries, all the coordinates are the same. And you can work it out the other direction. Obviously, if all the coordinates are same, every single element of ZP will obviously fix such an x bar. Okay, so is that clear? How we are arriving at this thing? In fact, if you have a non-zero I which fixes x bar, automatically you will get that all the coordinates in x bar have to be identical. Okay, so given any x bar belonging to x, one of the following happens. The first is, that stabilizer of x bar consists only of 0. Okay, and this is the same as saying that then the orbit, remember the orbit stabilizer theorem. Orbit stabilizer theorem tells you that the order of the orbit is basically the number of, I hear your, so if I take an x bar, then the order of the orbit is the index of the stabilizer in ZP. Okay, so that is order of ZP divided by order of the stabilizer of x bar, which here is P divided by the order of the stabilizer of x bar. So when the stabilizer of x bar has only one element, then that means the orbit of x bar will have P elements. Okay, so this is also the same as saying that the order of the orbit of x bar is P. And the second thing that we get is stabilizer, and also you can say at least 2 of the coordinates are unequal. And so basically every single element that x bar goes to under the action of elements of ZP, all of them are distinct. That's what this is saying. Or what can happen, stabilizer of x bar is the whole of ZP and this is equivalent to saying that the orbit of x bar only consists of x bar, and this is equivalent to saying that x bar has the form a comma a comma a for some a belonging to G. But please remember what happens if you have an x bar like this belonging to capital X. As long as this little a is different from identity, the moment you have this, this means a to the power p is identity. So this is actually equivalent to saying that a to the power p is identity. So what is our task? Our task was to find an a such that a in G such that a to the power p is identity, but that a should not be identity. Okay. So all we have to do is to show that there must be at least one orbit which has exactly one element, or equivalently that there must be at least one x bar, well, not one, an x bar where the a is non-identity such that the stabilizer of x bar is whole of Zp. Now let's see what we already know. We know that E belongs to G. Okay? Therefore, if I take E bar to be E comma E comma E, this definitely belongs to X, and we know that stabilizer of E bar will clearly be Zp, and orbit of E bar, orbit of E bar will consist basically of just E bar. Okay. Now we've done a result which tells us that suppose let O1, O2, and let's take O1 to be the orbit of E bar. Okay. O2, OK be the distinct orbits. Then we know that order of X is the sum I going from 1 to K of order of OK, OI. Okay, so this is 1 plus summation I going from 2 to K, provided there's more than one orbit of OI. Now let's look at this equation. Remember, order X is order G to the power P minus 1, right? And we know that P divides, we know P divides order G, all right? Therefore, what we get is sigma I equals 2 to K order of OI, 1 plus this is congruent to 0 mod P. Okay. Now, clearly, if there does not exist any A belonging to G minus E such that A to the power P is identity, then what must happen? Then we must have, see, remember what were the two situations? If you have an A such that A to the power P is identity, then the orbit has only one element. And if not, then the orbit has P elements. Now what you're saying is you've already removed the orbit coming from identity, 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 that P tuple. Now your aim is to show that at least one of these will have to have order 1. Now if none of these have order 1, what is the order they will all have? They'll have order P. Okay. Then we clearly have that order of OI is P for all I greater than or equal to 2. Therefore, what we'll get is 1 plus K minus 1 times P is congruent to 0 mod P. And that's a contradiction. Hence, there exists an A belonging to G minus E such that A to the power P is E. And that's Cauchy's theorem. So the idea is very simple. ZP acts by cyclically permuting elements of X, and we are just proving that at least 2 orbits will be there of size 1. That's all. That's the simple idea in this proof. Okay, so yeah.
Ma'am, we just want an element such that A raised to power P is E. We don't want an element whose order is P.
No, A is different from identity, no? So if A to the power P is identity, then the order of A will turn out to be P.
Yeah, earlier it cannot kill, like it cannot reach E before P. And
yeah.
Other than 1, yes, obviously, because it's a prime.
So the order of A will be either 1 or P.
Or yeah, it's a prime number, yes.
So that's why we need at least, see, we already saw that if you take the P tuple, which is E, its orbit has just one element in it, right? And so what you want is another orbit of some, you want to show that that orbit must exist, which has size 1. And if that orbit can have size 1 only if it is the orbit of an X which looks like A, where A to the power P is identity. And since you've already removed the E possibility, that was your first orbit, the second orbit that you get has to be of an A which is different from identity. And the moment you get an A which is different from identity such that A, A belongs to X, then obviously that is your element of order P that you want. Okay. So I'll finish with this part here, and now I shall try and do your, take you to a GeoGebra demonstration to show you how you can, it's a nice tool to visualize your symmetries and so on. And so let me move to that. So I'm going to stop sharing this screen and let me open a GeoGebra okay. Okay, let me see if I can share this. So can you all see the GeoGebra screen now? I'm sharing it.
Yes, ma'am.
And you can see whatever I'm doing on the screen, right? I've just dragged it and resized it. Can you see that happening?
Yeah.
Okay. So, so typically when you open GeoGebra, by the way, you can download freely, and it's also available in an app format that you have. So when you open a GeoGebra screen, when you open GeoGebra, this is the kind of thing that you get, and there's an algebra view and there's a graphics view. Now, what I like having a graph kind of a background paper, so I'm going to do that. I've added that. it helps me to make my drawings and so on. And of course, with any software, you should explore it. It's a question of self-exploration. And normally when I'm using software like this and I get stuck and I'm not able to do something that I want to do, then I find the internet a great source of answer. I just ask a question. And then, of course, you have to be careful in what source you look at for the answers. But if you're careful, you can actually find help very easily on the net. Okay. So I'm also right now going to remove the axis. I don't want it to show. And so I'll start out with something simple. I want to first explore symmetries of a finite figure, and I'm going to choose a regular n-gon. Now, the nice thing in GeoGebra is that it has all these features. So one thing you should remember in GeoGebra is that if you want to move whatever objects you're looking at here, you have to go to this move button. If you forget that, then it'll stay in whatever you have taken previously, and you will keep, you'll see as I'm doing, sometimes I forget, and then I'll get all these extra lines and stuff coming up. Then you have this tab, with which you can, make a point in your this thing. So here's a point. It tells you what the coordinate of the point. Even though I've removed the axis, it keeps track of where I've put the point. Okay. I'm just going to undo this. So here you have this choice of choosing a point or putting a point on an object. If there's a point already on an object, you can remove it. You can put a point on an intersection. You can choose a midpoint. Then it has something to do with complex numbers. Similarly, it gives you a way of drawing lines, segments, vectors, vector from a point, different types of lines, perpendicular, parallel, perpendicular, bisector, angle. You can actually explore, okay? But now I'm interested in drawing a regular polygon. And so I click on the regular polygon. And if you hold your arrow up, it tells you what you should do. It says, select 2 points and then enter the number of vertices. So I'm going to select 2 points, one here. And this is where having a graph background helps, because I can choose my points lying in a straight line. And I'm saying that I want 4 vertices because I need a square. So it's given me a square here. And then I want to explore reflections and rotations related to this square, right? I want to, and so you can do something really nice here. Of course, in order to be able to do the rotation about the center, I actually do need to find out the center of this square. So what I'll do is I'll first draw the diagonal. So I'm going to choose D and I choose B. And I've got the diagonal there. And then I can use the point choice that I have and choose the midpoint of this line. Okay, so I've picked up the segment E. It says this is segment E going from D to B, which were my diagonal coordinates. And when I click on this, it gives me the center of this line. And one of the nice things in GeoGebra is that you can actually hide all the lines. So if I just unclick this button, it'll hide the line, but still give me this E. And if I don't want the A, B, C, D to show, I can ask the label to be not shown. I can ask for one line of the, one edge to disappear. You can actually make something show or not show. You can rename. All of those things are possible. Okay, and so now I've got my square and I've identified the center. And what I'm going to do next is that I want to do rotations about E in the anti-clockwise direction, and I want to make a little animated thing out of it. So there's something called a slider that you can choose. So I choose this slider, okay, and I put it here, and it asks me what kind of a slider do I want, okay. So I'm going to name the slider, because it's an angle, I want to call it, say, theta. So theta is my slider, it's an angle, and this says it'll go from 0 to 360 degree interval, and I do apply, all right. And if you want to, so what you can do is this thing moves from 0 to 360 degrees. Okay, so I'll place it at 0 right now. And then you have this thing, which is all about how, all the things that we are interested in when we are looking at reflections. So you can reflect about a line, you can reflect about a point, reflect about a circle, rotate about a point. That's what I'm interested in right now. So I click this, and then you hold your arrow, it will tell you what to do. So if you want to rotate around a point, you have to select the object to rotate, and then the center point about which you want to rotate, and then enter the angle. So this is the object I want to rotate, and this is the point about which I want to rotate. And it's asking me by what angle do I want to rotate. Now, what I have to give here is whatever I've named the slider. I seem to have named it alpha. So let me choose alpha from here. So I'm choosing alpha, and I say OK. Now what happens is this slider determines the value of alpha. And as I choose alpha, I have to go to move, and then I choose alpha. It'll rotate. It'll start rotating. Okay. And you can see that when I've hit 90 degrees, the two copies of the square are matching. And again, I move, and the next matchup will obviously happen at 180. And then I move again, next matchup happens at 270, and then finally at 360 degrees. Now, if you actually want to keep track of, vertices, then what you'll have to do is, choose an off point thing, and then you can actually put vertices on this square, label them A dash, B dash, C dash, D dash, and then you can keep track of what goes where. Okay, but this is one simple way in which you can do your rotations with respect to a square. You can do this for any regular n-gon. You can do this for any figure that you draw, and so on. Now, what about reflections? Now, the thing with reflections is that, of course, you need a line to start off with. So let me take some arbitrary line, and I'll start by, I'm going to choose a line segment. Okay, I'm going to put it right now. Well, okay, wait, I don't want to really put it right in the correct spot right now. So let me do this first. So I'm still drawing a line segment, and I'm going from, okay, let me just undo what I did and restart with that. Okay, so F, and then my line is going to go till here. Okay, so this is my line. And suppose I want to reflect about this line. Obviously, I'm not going to get the square going back to it's this thing. So anyway, you can see that. This is just to show you that actually a reflection is taking place. Again, choose the object and then choose the line. And you'll see that a reflection has happened about that line, but obviously it's not a line of symmetry, reflection symmetry, because the two parts have not matched. But again, you can move this. So you can move this, and you'll realize that when you have when you're going through the midpoints of the two opposite sides, that's when your square will match. Similarly, you can check by taking the, you take any arbitrary line, you can rotate this line and then do your reflection and figure out all those things. And then what you'll realize is that there are exactly 4 positions which will give you your reflections, which is your vertical line, your horizontal line, and the 2 diagonal lines. So this is how you can explore symmetries of a finite figure that you want. You can, also you can also use, you can draw your own figure if you want and explore it. Okay, so you can use the pen and say I draw so I've drawn this figure, and you can again do all kinds of things about it. I mean, the way I've drawn it, it doesn't look very symmetric to me. It looks quite asymmetric to me, but you can check it out. In fact, that's a good way to check out. You can try and, draw a figure like this, do rotations and see if anything comes back. Obviously, rotations may not happen, but there is a slight possibility. No, I don't think there's any possibility. I think this one only has a 0-degree rotation. But the point is, you can draw any figure you want. You can import a figure into the system and then rotate it and so on. So let me show you. Let me just remove these, clear up my this thing. So I'm just going to remove the slider. I'm also going to remove my squares from here. Okay. So there, I've got a clean slate now. And what's left? D and E. I can't see them, so I'm just going to, well, they don't seem to be, this is what I said. So if you've not moved your pen from here, anything that you do will start giving you a pen thing. So go to move. And what I want to show you is about importing. And through that, I will also show you how to look at the, so when you're trying to look at symmetries of the plane, how do you keep track of it? Let me bring back my the coordinates. Okay, and so what I want to do now is so if you want to rotate the whole plane, or you want to reflect about a line in the plane, then the best thing to do is to take some object and to see the effect of rotating the plane or reflecting the plane by seeing what it's doing to that figure. Okay, so let me, you can again import an image by this. So this is an image that I'm going to import. I've already, the best often is to take an asymmetric letter like this. And again, you can move this around once you've chosen it. So I can move this anywhere that I want using the move thing. Say, let me position it here, maybe here. You can, resizing is a bit painful, but you can do that as well. So here's my R, and I want to maybe look, or maybe I'll push it a little more outwards so that you can actually see it better. And I already have one of these points. So maybe let me do a rotation of R about this point C. Okay, so if you, I can pick R, I can pick C, and I want to look at maybe a 30-degree rotation in the anti-clockwise direction. Right? So it shows you that R has moved. And obviously, if I move this R, its image, which is a 30-degree rotation, will also keep track. Okay, so, and when you click on this, it tells you, see, so this was called picture 1. And if you hover your mouse on this, it tells you that this is image, it's calling it pic 1 dashed, and it is nothing but picture 1 rotated by 30 degrees. So if you do a 30-degree rotation of the plane about C, then such an R will move to this position. Okay. Now, if I want to do a reflection, say, and maybe I'll choose a line this time through the origin. So I pick this and say it's this line. And I want to see, you can either reflect the rotation. So if you want to see what happens if you do a rotation of 30 degrees first, and then you do a reflection about this line, then you can, it's like first I do rotation, I hide my original image. So you can hide it by clicking on this and just removing the show object part. So my first R has gone, and I've got this rotated R. It'll still tell you that this is picture 1 rotated by 30 degrees. And now I'm going to reflect this about this line. So that means I've composed, I've done a rotation and then a reflection. So let's choose reflect about a line, which is this. So I choose the image and I choose the point. And this is the reflection. And you can get back the image that you had earlier, and you can see what has happened as a result of doing a 30-degree rotation and then a reflection after that. And one other thing that you can do here is translate by a vector. So maybe now what I want to do is I'll make this also disappear. I don't want to see it right now. And I don't want to see this line either. But now I have this image, which was what? I started out with a 30-degree rotation. Then I reflected about a line F, which was called F through the origin. And, line G through the origin. And then now I'm going to apply a translation to this. Okay, but for a translation, I want to translate by a vector. So first I should choose my vector. So let me draw an arbitrary vector. So maybe this is the vector I want to translate it by. You can, of course, change the direction and everything by moving this K. It allows you to, scale, reduce, do all kinds of. So maybe my eventual vector that I want to translate it by is this. If I take too much of a magnitude, it will go beyond my screen. So here I can translate by the vector. So again, it will say choose the object and then the vector. So I've chosen my object and then the vector, and you'll see that it's showing you where the R will move in your translation. So one of the things that happens is that, so the question is, if you're looking at the symmetries of a plane, we've already seen that you can have reflections, you can have rotations, and in fact, I mean, one of the things that Amit did in his lecture was to show you that any rigid motion, so a symmetry of a plane is nothing but a rigid motion. And he told you that every rigid motion is the composite of a translation and an orthogonal transformation, right? So when we are looking at rotations about the origin or reflections about lines through the origin, that collection forms a group which we call the orthogonal group, right? And you saw that in the matrix form. It was the collection of all matrices A such that A transpose gave you identity. So in fact, every rigid motion is just a composition of these two things. But if you want to in a sense think about what are the different types of symmetries that you can have, so obviously you can have rotation about any point on the plane. All right, you can have reflection about any line in the plane. Then you can translate by any vector. That again gives you a symmetry. And the collection of all symmetries, remember, forms a group, which means that if you compose any two of these, you should come back to a symmetry again. Now, the thing is that there is still one composition which doesn't come back to these three. So if you start out with a translation and then do a reflection, or do a reflection and then a translation, at most of the time, it is not going to come back to being either a rotation or a reflection or a translation. It gives rise to a new kind of symmetry, which is called a glide reflection. Okay, and you can actually define the glide reflection in its own terms, but typically it's best to just think of it as that when you compose a translation and a reflection, except under some special circumstance, it is always going to give you a glide reflection. And glide reflections and reflections are what are called orientation reversing. Basically, in the case of the reflection, that's essentially the same as saying that its determinant of that matrix is -1. Okay, so whereas translations and rotations are seen to be orientation preserving. And the collection of all of these symmetries, right? All the possible rotations, all the possible reflections, all translations, and all glide reflections is the collection of all rigid motions of a plane. And you've already seen that in what kind of a structure it has as a group. It is, there is the group of all translation. Well, you can see every single rigid motion can be written as a translation composed with an orthogonal transformation. Okay, so that's, and again, so the GeoGebra provides you of a way of keeping track of, what really is happening. One nice way to see all the compositions. So for example, you've already seen that if you have two reflections of a finite planar figure, then obviously they intersect at the center, and then their composition gives you a rotation. Okay, so you can think about general things that are going to happen in a plane. So if I take two arbitrary reflections about two lines in a plane and I compose them, what will I get? And the answer is different depending on whether those lines intersect or they are parallel. So think about it a little bit. If you have two reflections which are going to intersect, then it's pretty much same as what is happening in a finite planar figure. So I mean, it's like what might be happening within a regular n-gon type of thing. So what you'll get is that those two reflections, when you compose them with one another, will give you a rotation of the plane. On the other hand, if you have two parallel lines, and you're doing a reflection about the first one first. In fact, we could probably see that quite easily here. Okay, so let me, this is what I meant when I said that if you stop using the move button, then it creates a lot of problems. So let me remove this. and instead bring in my R again. Okay. So again, move button. Let me remove the axis here. And let me, okay, so here is this R is going to allow me to keep track, and I want two parallel lines about which I'm going to do my reflection. So let me choose two segments which are parallel, and I'm going to keep them vertical. It's just easier to deal with it. So this is one line, and then I have another line here, and I want to see what the net effect is of reflecting this R first about this line and then about this line. Okay, and you'll see what happens. So I reflect this about this line. I get that. And now I reflect this about this line. And the net effect is that this R has got translated, right? And what is, how can you check that? You can, actually see how much the translation is. It's basically gone from here. Oops, sorry. Let me place this here. And then this was the starting point. And then it's gone all the way up to here, right? I mean, you'll have to adjust this a little bit so that you're in the correct spot. But you can check that this is a translation by doing this. So I start with this, and then I choose this. And actually it has translated. You are not able to see this until you hover. So when you hover, you can see this was definitely, first the reflection of, and then another reflection. So that is the first thing, picture 2 dashed mirrored at I, it's saying, because it's a mirror image of this about I. And it's also picture 2 dashed subscript 1, which is translation of picture 2 by V. So this was picture 2, I reflected it. So this was picture 2, I reflected it, and I got picture 2 dashed, which was reflected about the line H. And then I reflected this about line I, and I got this. But then when I translated R by this vector, then also I came here. So this tells you that if you're going to reflect, I mean, this is not a proof. That's one of the things that I want to mention. This is only a tool by which you can visualize what is happening. And then of course you'll have to prove it. But this tells you that if you're going to reflect about if you're going to follow a reflection by another reflection, which is about two parallel lines, then the net result is that of a translation. Similarly, you can figure out what happens when you compose two rotations. Does it matter whether the rotations are about the same center or about two different centers? That's something to think about. What happens when you compose a rotation and a translation? What happens when you compose two translations, and so on? Okay, so this gives you a way in which you can work with these things. And now let me tell you a little bit about strip patterns. And since it's too much of a hassle to remove all of these, I'm just going to start with a new okay, sorry, cancel. Or maybe I'll just call this R, and I'll start a new file. Maybe one which I have already done a little bit on, so that I save some time. Just give me a second. Okay. So again, let me share my screen. Okay, here. So this is something which I drew using the pen tool. And then I just copied it and pasted it and I've pasted it. Like if you look at this point and this point, I've basically taken 3 squares. So they've been placed at equal intervals. And you have to imagine that it is continuing indefinitely to the right and indefinitely to the left. So something like this is what is called a strip pattern, right? So how do you construct a strip pattern? You choose your motif, whatever it is. It could be a square, it could be an equilateral triangle, it could be a flower that you have drawn, or some picture which you have found attractive and imported. And basically you place it, you think of the number line and you're placing it at equal intervals on that number line. Okay, and what you get is a strip pattern. Now, what we are interested in is what are the symmetries of such a strip pattern. Okay, now if you look at finite figures, so finite planar figures are those, intuitively you can just draw a rectangle around them, you can box them. But this is an example of an infinite figure because it's going to continue indefinitely to the left and the right. Right. So this is an example of a non-finite figure, and technically the definition of a finite figure is if it does not have translation as a symmetry for it, then it is a finite figure. That's the technical way in which you can decide something is a finite figure. But you can see that the way in which a strip pattern is constructed, obviously it is going to have translation symmetry, right? So how can I look at the translation symmetry aspect of this? So let me, so you have to figure out how much to translate by. So there is this point. So let me place the point, or maybe I already have that point. 1 second. I had, let's see if I'm getting back. Okay, A and B. No, these are not the points I wanted. These were something else. All right, so let me mark some points. So I mark a point here and the corresponding point in the next figure. All right, so these are the distance between this is the translation that I'm interested in. So I want my vector to basically start at D and go to E. All right, and I would like to move this below. Oh, okay, so it's attached. So let me detach the points. I don't want to attach it to that thing. I detach it, I detach this, and let me move this below so that you can see. Hopefully this is, it doesn't look, okay. I mean, now it's horizontal, right? So I want to show you how this strip pattern is going to have this translation. Okay, so I choose the strip pattern first. So I choose it, and then I want to look at translate by vector. And this is my object which has been chosen. And this is the vector about which I wanted to translate. So you can see there's a slight error that's coming because I've not measured the length of the length of this. You can adjust this vector and then actually do it. Yeah. Okay. well, I've either not placed the strip properly or okay, modulo minor errors. You can see that this is actually a translation of the strip pattern. Okay, now the question is that if you take a strip pattern, there will always be translation. And so I also want to write something related to this. So I'm going to go back to my this thing and share a different screen with you. Right. So the point is that when you're dealing with strip patterns, so when I want to look at strip patterns, it will always, so there's a basic translation. So the one that I showed you in the strip pattern, and I'm going to call that vector. It's translation T, and I'm translating by a vector little t. Okay. And so you can pretty much very quickly see that all these are also going to be translations. So when I say t square, I mean apply t twice. Okay, t cubed and so on. And then obviously, if I apply t going in the same magnitude, but the direction reversed, that is, I translate by the vector minus t, then I'll get the inverse translation, t to the power minus 2, and so on. So if I start out with a strip pattern X, there is a basic translation that I can do, which will always be there for such a strip pattern. And what you see is that the cyclic subgroup generated by this T is always a subgroup of the symmetries of the strip pattern. Now the question is that, I mean, obviously the basic motif that you're going to choose will determine, you know, whether you have any other symmetries or not. So for example, in the one that I have chosen here in the GeoGebra screen, I'll just undo my translation so that I don't have this. Okay. So the strip pattern that I've taken here, you can see that my basic motif is asymmetric in the sense that the only symmetry that it possesses is the 0-degree rotation. So when you create something like this, then obviously you cannot expect it to have, as Amit said, it will not cause you too much confusion, right? If I do rotations of this, I mean, one thing you should remember is that if a strip pattern has a non-0-degree rotation, then it has to be a 180-degree rotation because it has to come back looking exactly the same as it is. And then you can ask it, you know, it could have vertical lines of reflection, which in this case it will not have. This also does not have a horizontal line of reflection. But you can actually starting from a strip pattern with, you know, with a very asymmetric basic motif, you can actually create strip patterns with more symmetry in them. Okay, so I'm just going to show you a way of doing this. So suppose I choose A and I want to say create a strip pattern which has 180-degree rotation in it, and where basically obviously translation will also be always there. Okay, but maybe I want to create something which just has 180-degree rotations and translations. So what you do basically is that you choose one of these, choose a point, say I've chosen this point A, and now I'm going to rotate this. I want to rotate this about this point A. And I want to do a 180-degree rotation. Okay, so I get this figure. Then I hide this one. I don't want this, so I'm going to hide it. And I choose the next point, same corresponding to this. This was my point, corresponding to this. This is going to be my point. And I do the same thing. I rotate this by 180 degree. I get rid of this one. Okay. And then I put my next point and do a rotation by 180 degree. I get rid of this. Okay. This new, and then I get rid of my A, B, and my C. So this new strip pattern that we have here is one. So what is the basic motif now? The basic motif is actually this much. This is my basic motif. And if you look at this, this has a 180-degree rotation for it. And all I've done is I have placed this basic motif at equal intervals. And now this new strip pattern that I have, is one where I definitely have 180-degree rotations about centers. You know, there are many such centers. There's this, I can have this as a center, or I can have this as a center, or I can have this as a center. Those points A, this is a rotocenter. Similarly, this is also a center of rotation, and so is C. So you'll have infinitely many centers of rotation, all lying on that horizontal axis between these two things and at specific points. If you move the center of those points, you will no longer get a symmetry of the strip pattern. Now, the question is, what is the group of symmetries of such a strip pattern? So again, remember that the strip pattern is sitting inside your plane. So the different types of symmetries you can have are either reflections, rotations, translations, and glide reflections. Okay, so these are the main things that you can have, and then you can try and figure out what are the symmetries that this thing actually has. Does it have a glide reflection, for example? So a glide reflection, remember, is it comes about when you translate and reflect. Okay, so is there a translation that I can do and then do a reflection which will bring me back here? Now the point is that reflections about horizontal lines are not really going to work very well in this particular thing. You will see that. I'll just show you. So if I take a horizontal line, the same one where I used to have, let me just place this here, and then okay, wait, this is not working. It's fixed it as a point. So let me remove this and instead start with the line. Okay, fix 2 points. I fix. Right. And let me again choose this entire strip. Okay, and now I want to do reflect about a line. reflect about a line. So let me choose this line. It chose the, well, let's see, what has it done? No, it hasn't done this. Let me just do this again. Choose the object. I've chosen the object and I have to choose the line. So I've chosen the line now. And you can see that this was not a symmetry of the strip. However, I've created a new strip now. You can see by this, you've actually created a strip now which has what? Also a horizontal reflection thrown in. But that's not what I intended to start off with. So I'm just going to undo this. And then I will undo my line. All right, so this particular strip pattern is only going to have your positive orientation symmetries. So this will have 180-degree rotations and it will have translations. So now think about what kind of, and obviously that collection has to give you back the group of, that collection forms a group. So let's again go back and explore this a little bit more. This seems to have 180-degree rotation, remember, is order 2. So there are infinitely many order 2 elements in this group which are coming from 180-degree rotations. And then there is this translation, the cyclic group of translations where T is your basic translation. Okay, so let me stop sharing this and I'll go to this and let's just explore what we have. So I want you to recall that when you are looking at the regular n-gon, we called its group, this was the group of symmetries. Of a regular n-gon. It basically had n rotations and n
Excuse me, ma'am.
Yeah.
Are you sharing your screen, ma'am?
No, I forgot. Just 1 second. Yep. Thank you for reminding me. Yeah, can you see? I've written Dn is the group of symmetries of a regular n-gon. There are n rotations and n reflections. And you've seen now that, and you can think of these. So you can think of the regular n-gon centered at the origin of your plane. And so the reflections and rotations of the regular n-gon are nothing but rotations about the center of particular angles and reflections about lines through the origin. Okay, so this is sitting inside your group of isometries or the group of rigid motions of the plane. And you already saw from Amit's lecture that you could write the elements of the orthogonal transformations as matrices, 2 by 2 matrices. So one of the questions that I've asked you to do in the tutorial is that if you're looking at the symmetries of a square, there are 4 rotations and 4 reflections, write them as 2 by 2 matrices. The rotation and reflection matrices associated with rotating and reflecting about suitable lines. But today, just now, what I want to do is to quickly write down a different way of looking at Dn. It's called a presentation for Dn, but I'm not going to go into the theoretical detail of why this is a presentation. Basically, this is a format in which you give generators and relations. So I'm going to write this as x comma y such that, and I'll explain what this means, x square equals y to the power n equals 1 and xy x inverse is y inverse. Okay, so basically at your level, the way you should interpret this is that this is a group generated by an element X which has order 2, element Y which has order n, and the relation between X and Y is given in this way. That is, if I conjugate Y by X, then I get Y inverse. And how does it match up with what you knew before? This Y is your basic non-zero degree rotation of 2 pi by n. And this is any reflection. And you can check that they will satisfy these conditions. And you can actually write down all the elements of dn as 1, y. So in D4, for example, y is r 90 degrees. And so you'll have then r 180 degrees, which will be y square, y cubed. And of course, there y to the power 4 gives you identity. And in a general regular n-gon, you have these n rotations. And then you have the n reflections. And they're nothing but the composition of a reflection and y square, and so on. X, y to the power n minus 1. These are your n rotations, and these are your n reflections. Okay, and so here's a question. What is the symmetry group of a circle? Of a circle. And now let's come to what the strip that I showed you earlier. I'm going to claim that that if I choose, so this is what I call my shoes, the second shoe strip. Okay, that's my X. We saw that it has translations and 180 degree rotations. Okay, and I'm going to choose, I'll call my translation, basic translation, as Y now. And I will call any one of these rotations that I have as X. And you can cross-check that, of course, Y has infinite order, right? But X square is 1. And you can cross-check that the symmetries of X will turn out to be, again, the group generated by X and Y, such that X square equals 1, and with the condition that X inverse is Y inverse. And this is called D infinity. Okay. So it turns out that the symmetry group of that particular strip that we talked about is D infinity. And very quickly, I'm just going to show you a page of from Gallian, the book Gallian, which actually tells you about the different types of strip patterns that you can have. There are only 7 types, and it also tells you what the associated groups of symmetry are. Of course, it's a tutorial question that I've given you to find the groups of symmetry. Gallian only gives you the answer there. What you will need to do is to actually figure out that those are the groups you actually get. So let me stop sharing this and quickly share with you a screen from, okay, I'll first have to find it. So just give me a second. Okay. Now I should be able to show you. So this is from Contemporary Abstract Algebra by Gallian. And you can see that he's talking about the 7 frieze patterns, and their group. Frieze is also another word which is used for strip patterns, and their groups of symmetry. So he's, if you can see, he's again chosen a asymmetric figure, which is R. And this is like the first shoe strip that I had, and it has only translation. And so the group of symmetries is the cyclic group generated by this element X, the basic translation, which has infinite order. So the group that you get will be an infinite cyclic group, and so you get basically integers. It's isomorphic to the integers under addition. Then this particular strip pattern has been, how do you construct something like that? You translate this little r to this much, then you reflect it. So that's like a glide reflection. And your basic motif then becomes your upturned r and the bottom turned r. This is your basic motif. And so in the glide reflection, you're going half the length in its translation, not the full length. The basic translation is the full length. So here, what if you take X as the the half length the translation, which he's called the glide reflection, then that is enough to generate the entire group of symmetry. And that gives you again isomorphism class, which is Z. So even though these are two different strip patterns, they have the same group of symmetry. So you can't use the isomorphism class of the group of symmetries to distinguish between the strip patterns. Okay, and then, I mean, so these are the one that I looked at next. The second shoe strip pattern was what is called type 4. It has translations and rotations of 180 degree, and together they give you D infinity. And you can see that there are 7 types. I will leave you to explore these. And I've given you a way in which you can actually construct each one of these yourself. We already saw, well, we saw one, this thing already in the process when I did that horizontal reflection. Okay. So you do use Gaussian for your abstract algebra course. Of course, the chapter from which I've taken this is comes in the latter part, and you can go there and read a lot more about frieze patterns. How do you find its groups of symmetry? And also, is there a nice algorithm for figuring out, which of these 7 types of strip patterns that you actually have? So if you're given a strip pattern, how do you use some kind of a nice algorithm to classify it? All that is there in Gaussian, so I would urge you to look at it. And I will stop here today. Shweta, I think I've stopped in time.
Yes, ma'am. Yes, ma'am.
Okay. So, I guess you need to go
3D figures in GeoGebra.
So there is 3D as well possible in GeoGebra, but I've not really explored it. But it does have ways of doing 3-dimensional figures as well.
Okay, ma'am.
So you can do that. I don't think you should have a. I mean, though I'm not very. See, if you just search on the net for drawing 3-dimensional, say, Platonic figures in GeoGebra, you will get that. Okay. The other place where you can definitely draw them is using Mathematica. So that's another software that you can use. And with Mathematica, I mean, so the advantage with GeoGebra is that these things are really built in very nicely, at least for planar figures, which I have explored. I've not really explored GeoGebra for three-dimensional figures, but I'm pretty sure there must be a capacity to do it. Mathematica, again, of course, it's a proprietary software, but you can access it freely on the net. There's something called Wolfram Cloud. And if you just sign up on it, you can open Mathematica notebooks in your account, provided you're connected online. And Mathematica also has a very good visualization that you can do for three-dimensional objects. You can draw it, you can rotate it, and all of that is there. But it's not, you'll have to do, you have to give you have to put in a more effort there to even draw those things. And in GeoGebra, you already have a key, which gives you a way of drawing a regular n-gon. Whereas in Mathematica, you might have to actually figure out how to do that kind of it's more using coordinate geometry and so on. So, but these are both things that you can explore.
Yes, ma'am. Thank you, ma'am.
You're welcome. Anything else that someone wants to ask? I mean, for those of you who are not good at mentally rotating things and doing stuff, I would actually urge you to use GeoGebra, because it gives a visualization to something you're not being able to think of in your head. So it helps you as a tool, but please don't see it as a proof of anything. Okay, so if you want to actually prove that, if you have two rotations whose axes are lines of reflection are parallel to each other and the composition gives you a translation, then what GeoGebra is doing is not giving you a proof. It's only giving you an intuitive feel for what is happening, right? The proving is something else that you will have to do.
Excuse me, ma'am. I had a doubt.
Yeah, Hiba.
Ma'am, so ma'am, you said that the translation, ma'am, it can go up till infinity, but ma'am, in the group isomorphism class, ma'am, it is written as integers. Ma'am, why cannot it be d infinity?
So just in the first case, in which strip pattern are you? The first strip pattern I showed you, in that you're asking?
Yes, ma'am, the translation.
So in D infinity, you have infinitely many elements of order 2, remember. In D infinity, when you're, what I wrote down as D infinity, I had taken Y as the element of infinite order. So cyclic Y is like Z. And I had X as the 180-degree rotation, right? But when you're looking at the elements of that group, they will be 1y, y square, dot, dot, dot. And you'll also have x, xy, xy square, xy cubed, dot, dot, dot. And all those x, xy, xy square, xy cubed, and so on represent 180-degree, different 180-degree rotations. They all have order 2. Now in Z, you don't have any element of finite order except 0, right? So obviously D infinity and Z are very different. And in the first strip pattern I showed you, there was no element of finite order. There was only a translation and powers of a basic translation, and then the integral powers of that translation. Because you remember what is happening in the vector. So the capital T translation means move the strip by, translate by along the vector little t. So when you do t square, that is apply t twice, capital T twice, that's like doing a translation of the vector to little t. And when you apply t, capital T thrice, that's like translating by 3 little t. So you can only, if you translate by non-integral multiples there, you will not get a symmetry of the strip pattern. The symmetry of the strip pattern is only occurring when you translate by an integral multiple of that vector little t. So in the first strip pattern I showed you, there was only translations involved, and therefore you end up getting that its group of symmetries is integers. In the second strip pattern that I showed you, which was the fourth pattern in Gaussian, there what happens is that you have two generators. One is the translation, which has infinite order, and the other is the 180-degree rotation. Together, they generate the whole group.
I think some problem.
In Gaussian, because there the generation was by an element of infinite order, which was your translation, and you had a 180-degree rotation, which had also satisfied the relation that when you have xy x inverse, you get y inverse. So together, the group that they generate is called D infinity. And when you're only looking at a translation subgroup, that is isomorphic to Z.
Yes, ma'am. Thank you, ma'am.
Welcome. Anything else? Yeah. Okay, then Shweta, should we take a break then?
Yes, ma'am. Yes, ma'am. So, ma'am, I messaged him for about, like, let's see, 11:40 around.
Okay. Yeah, at least you should get a 15-minute break.
Yes,
Everyone
yes.
needs it, including me.
Okay.
Okay. See you people later. Bye-bye.